You are looking at the golden mirrors of the biggest and the most complex telescope built to date, the James Webb Space Telescope. These mirrors will look at those regions of the cosmos that no other telescope in the past could. They will show us how the cosmos looked just 200 million years after the Big Bang and help us understand the formation of the first galaxies. But how exactly is Webb going to achieve that? What is it so special about the 18 hexagonal mirrors of the telescope that make it the most incredible space telescope humans have built to date? For any telescope out there, the primary mirror is like its heart. The primary mirror is the one that captures all the light from distant sources. And this light is further processed to produce breathtaking images of the cosmos wonders beyond us. However, this is possible if and only the mirrors are designed precisely. When the Hubble Space Telescope was launched, a small error in its primary mirror made all the images fuzzy. As a result, NASA had to send a team of astronauts to fix the telescope. But we can't afford to make the same mistake again, because James Webb will be placed much further in orbit. Fabricating a telescope's mirrors is not a cakewalk. Many factors need to be taken into account during their fabrication. First, the mirror must be lightweight, yet extremely sturdy to withstand the pressures it is subjected to during its launch and overall journey. So to realize these properties in Webb's mirrors, beryllium was used. But why beryllium? What's so special about this element? Beryllium is a light metal that is very strong for its weight. It is a good conductor of electricity and heat and is not magnetic. Moreover, beryllium is extremely good at holding its shape across various temperatures, making it desirable for manufacturing Webb's primary mirror. To construct the mirror, a finely powdered class of beryllium, 030, was used. But as I told you earlier, it wasn't a very immediate process. The mirror segments were first brought to life at beryllium mines in Utah, and after that, they were moved across the USA for processing and polishing. Webb's primary mirror is a giant beast, significantly larger than all the mirrors available on the current generation of space telescopes. In total, the primary mirror is composed of 18 hexagonal-shaped mirror segments. Each of the segments is 1.32 meters in diameter and weighs approximately 20 kilograms. In addition to this, the convex secondary mirror is about 0.74 meters in diameter, giving the James Webb Space Telescope approximately 6.25 times more collecting area than the Hubble Space Telescope. As we know, Webb is broadly going to work in the spectrum of infrared frequencies. So besides being made up of beryllium, each of the telescope's mirrors have been carefully covered in a highly uniform and microscopically thin layer of gold. The gold coating optimizes the segments specifically for reflecting infrared light and makes it even more efficient. But why did we particularly choose 18 hexagonal mirror segments for the James Webb Space Telescope? Why not 10, 12, or 15? Moreover, we could have gone by circular or square-shaped segments. So why only hexagonal segments were chosen? There's a simple but logical reason behind this. The power of a telescope directly depends upon how big its primary mirror is. The larger the primary mirror, the greater the amount of light collected, and its observations will be better. Now looking at James Webb's bucket list of future observations, it needed a giant primary mirror. But there was a problem. A mirror so large could not fit inside any of the existing rockets as one single mirror. So what now? Well, this is when the team came up with a revolutionary idea to disassociate the primary mirror into 18 small segments that can fold to fit inside the rocket fairing. Secondly, a roughly circular mirror shape is desired to focus the light on the detector's most compact region. There are complications associated with other geometries. For example, an oval mirror produces elongated images in one direction, while a square mirror sends a lot of the light out of the central region. For this, An approximately circular shape was required for Webb's mirrors as well. Now coming to the hexagonal shape. It has a six-fold symmetry. This gives it a high filling factor, which further assists the segments in fitting together without a gap. So, a honeycomb-like pattern allows each mirror to perfectly fit together with the least amount of dead space in between each other. This effectively creates a singular and massively powerful unit and produces the desired approximately circular shape of the primary mirror. Okay, so now we have 18 mirror segments with us. But the story doesn't end here. Rather, here comes one of the most complicated steps of the process: aligning and focusing the segments perfectly as a single flawless mirror. And this is where actuators come to work. Actuators are tiny mechanical motors that beautifully work to achieve a single perfect focus. In total, Webb's primary mirror segments and its secondary mirror are moved by 6 actuators attached to the back of each mirror piece. Moreover, the primary mirror segments also have an additional actuator at their center that helps in adjusting their curvature. All the actuators have been designed to make adjustments precisely without disturbing the other segments. This allows Webb's mirrors and other instruments to work in a perfect combination to create compelling and error-free observations. Speaking about the fine engineering involved in the construction of Webb's mirrors, Lee Feinberg, who is the Webb Optical Telescope Element Manager at NASA Goddard, once said that aligning the primary mirror segments as though they are a single large mirror means each mirror is aligned to 1/10,000th in the thickness of a human hair. What's even more amazing is that the engineers and scientists working on the Webb telescope had to invent how to do this. As discussed earlier, the James Webb Space Telescope will primarily work in the range of infrared wavelengths. Infrared radiations are nothing but an object's signature in the form of heat. This means that every object at a non-zero temperature would emit some infrared radiation. So if Webb's mirror is kept at the same temperature as the Hubble Space Telescopes, then the faint infrared light from distant galaxies would get lost in between the infrared glow of the mirror itself. So, to get rid of this interference, Webb's mirror will be kept at around -220 degrees Celsius. Achieving this temperature is another critical task, and to do the same, the telescope will have a 5-layer sun shield that is the size of a tennis court. The giant sun shield will weaken up the heat from our host star by more than 1,000,000 times, helping achieve the desired temperature. With its mirrors being several times more advanced and powerful than all the space telescopes launched so far, Webb is surely going to be a beast in the arena of astronomical observations. Webb is going to curate a history of its own.